Hi everyone. I want to say a few words about neural rendering. Who knows what is neural rendering? Hands up. Perfect. I hope that at the end of the talk, all the people say that I know what is neural rendering. But the main goal of neural rendering is to produce 3D objects. And you know, there is a problem with 3D objects dedicated for games or VR or other 3D engines, because you know you need a lot of graphics who build the nice shape and texture, and you need a lot of time to produce it. And you know, deep learning wants to substitute this guy by neural networks. So the idea is to take simple photos, 2D or video from the mobile phone or something like that, and produce the full object, 3D object, which can be put to the 3D engine, games, VR, or something like this. And the main goal is to produce the object which is extremely realistic. So we want to produce extremely realistic objects which can be added to the 3D engine. Yeah. So how looks the pipeline? We start from taking something which is real. We take some photos of the objects. Of course, we need a few images. Some modern techniques can do it from 1 or 2 images. And after that, we forget that we have a real object, and we want to produce 3D object which goes to the 3D engine. Yeah, so we have images, 2D, the classical or the video of the object. We applied some computer program, neural rendering. I will talk about it. And after that, we obtain the correct renders in our engine. And the first or the most important algorithm for this is neural radiance fields NeRF. Who knows what is NeRF? Great. So I only say that in general, instead of keeping mesh with texture, some physical object, we have only neural network, which transform 3D points from the 3D space into 3 numbers, RGB color, 4 numbers, RGB color and transparency. And it is trained quite simple. We have few existing images, the input to our model. We take some rays which goes from the camera position through the image and goes through the 3D objects. We sample some points on the ray, and we train our neural networks to produce each 3D point, 3D RGB color and transparency for each point, and we aggregate, we average this point, and we train it that the correct pixel color is as close as possible to the average number of this prediction of the neural network. When we finish the training, it's quite simple. In the 3D engine, when we have some camera position and we want to produce the object, we have the white card, and produce a lot of rays which goes through each pixel of our scene, and we sample point from the ray. We run the network to predict the color and transparency, aggregate it, and we obtain the color of each pixels, because the net was trained to in this way that aggregate numbers, aggregate information to the ray, produce the correct color. In the inference, it's work the same. And this algorithm is quite effective, but have some problems. The first problem is that the camera in 3D space all the time is changing, so the neural network should produce this pixel all the time, and you have to sample a lot of points, and it takes a lot of time. So the rendering is, of course, maybe not because it is possible to do it in real time, but it is quite expensive. Yeah. And also there is a problem with modification, because if we have the mesh, not neural network, we can take part of the object and move them in 3D space. It is quite hard to say to neural network to change the weights of the network to produce some simple change in the 3D object, for example, removing some elements. So the pipeline is quite easy. We have 2D images. we need the position of the camera. There exists algorithm for it. It's quite old. When we have the position of the cameras, we train NeRFs or other algorithms, and we obtain, it called novel views, because when we put the new position of the camera, we obtain novel views. And recently appears 3D Gaussian splatting algorithm. Who know what is 3D Gaussian splatting algorithm? Great. So the algorithm is nice because it's quite simple. I can say this is not a deep model, yeah, because we have only means, the center of Gaussians, covariance matrix, so the shape of the Gaussians. Each Gaussian has color and opacity. So in practice, we can think about RGB color and the opacity. So we have a set of Gaussian. Of course, we draw it as a convenience ellipses, so we can see here ellipses. And you know, when we have the neural networks, when we have NeRFs, we don't have any real object. We only have the neural network weight. And these networks produce a correct views. Yeah? Here is the same situation, but instead the neural network, we have these Gaussians. And they exist, but you know, they are quite messy. We need to splat them or project them on the plane, and we obtain the real world high quality images. So to understand Gaussian splatting, we need to understand that we have Gaussians, so ellipses with colors and opacity, and some algorithms, easy and effective algorithm produce the high quality renders. And the algorithm is quite easy because when we have ellipses, this Gaussian distribution, so exists the closed form formulas to project the Gaussian to the plane. So we project the Gaussian to the plane, and when we have a lot of Gaussian, we average the color of the Gaussian. So the stain is constructed from the lot of Gaussian distribution. We project them on the image, average this value according to some formulas, and we obtain a real life object inside some 3D engine. And you know, the Gaussian splatting is as simple as possible. Yeah, we have only the centers, covariance matrices, colors, and opacity, and we can train it very fast. For some high resolution scene, I have the half of the hour is enough to produce. And in our team, we work with Gaussian splatting, and we produce some papers which I want to talk about. The first one is games, because you know, when we have Gaussian splatting, the first idea is to trick them as a video as a meshes. So we want to take the Gaussian and move them in 3D space. And it occurs that it's not as easy as it looks, because when we move Gaussians and we move the centers of the Gaussians, it is not enough because the covariance matrix shape is not adapted correctly. So to move the Gaussian in 3D space, we need to find the normals or find the covariance shape or find the way to modify the Gaussians. And in practice, it's quite problematic. And in our works, we want to convert Gaussian splatting to something what is similar to the mesh. So meshes are nice because when we have a meshes instead of Gaussian or neural network, we can take some elements, move them in 3D space. So we tricked the object as a point cloud, and we want to put the Gaussians on the surface of the object, and we use the flat Gaussian. So this is the Gaussian where the first one of the components is almost zero. So it is flat. And we try to put this Gaussian on the object as close as possible, because if they are posed like in the mesh, we can take them and move in the 3D space. So we need to produce some modification of Gaussian to be able to move the mesh to obtain this kind of modification. And the main idea is quite simple. When we have the Gaussian component is a flat, so the normal is almost zero. So we can very easily find the triangle which describes the object. So it is enough to find the center of the Gaussian and find the main components of the Gaussian distribution, and the first component gives the first point, the second one is here, but we orthogonalize them. So this is the second component. The third one is the orthogonal one, this flat Gaussian. So it is easy to recalculate the parameters of Gaussian distribution into mesh phase. And of course, we can do it reversely. So if we have a triangle, we can calculate the Gaussian, which looks like the triangle, because we can take the center of the vertex of the triangle, and we can produce the covariance matrix by covariance of these 3 points. And this is constructed, and we can produce a lot of Gaussian dedicated for one phase by scaling the Gaussian by some scale. It's the same shape with different scales. And it works in this way that when we move this phase, our Gaussians are moved according to the phase change, because they are parameterized by the vertex of the mesh. So we can take the mesh and modify the mesh in the mesh way, like it was done before neural rendering, and the Gaussian are adapted correctly. And our model can be used in 3 main approaches. The first one, when we have already produced a mesh. I know that it's quite difficult to get the mesh, because if we have a mesh, we don't need to do almost anything. It is enough to produce the texture. But if we have the mesh, we can train only the Gaussian on the mesh face, and we obtain Gaussian splattings on the mesh, and we can move the mesh, and everything works correctly. Of course, the more complicated situation when we don't have a mesh. So we can get some prototype of the mesh. For example, when we have phase avatar, there exists the universal phase avatars, and you try to feed them to the model. So in this way, the vertex of the universal avatar are trained, and the Gaussian are trained, and we are able to feed Gaussians and feed the mesh to the phase. And the third application is that we don't have any information about the mesh, so we have only the images. So then we train the Gaussian. The Gaussian are converted in the triangles. The triangles are disconnected, so we called it, or it's called in literature by triangle soup. So in fact, we have this disconnected object, and we can move this object in 3D space to obtain some modification, like the point cloud. Of course, it is problematic, so we can approximate this Gaussian by some simple mesh, and simple or more accurate mesh. And when we parameterize this Gaussian by the mesh, we can modify this large mesh to control the Gaussians. And it occurs that Gaussian splatting, the games work great. We can modify the triangle soup mesh or whatever we have inside the model, and we obtain the real life modification. The second paper which I want to talk about is Przemysław. It was published on NeRFs, so and I know is happy in general, and it is dedicated for dynamic scans. So we have some scan which already is moving. For example, this dino is open the mouth or something like that. And we add additional modification. Here we have the wave ground or something like that. So our goal is to modify dynamic scan. And working with dynamic scans is quite a popular old task, and exists a lot of methods which allows to model this dynamic scan. So people try to construct approximate this dynamic scan and allow the modification in each frame. And we compare our method with Versatility, so the method which was published in CVPR this year. And it allows the modification by using control points. We need to add some static points which mark the element, which force the elements to be static, and dynamic ones, and we take these points and move them, and we obtain some modification. And it occurs that this model has some limitation. For example, when we take this hand and move the head also was modified. It is problematic. We can also make the hand very long. I don't know why, but if we do it, the algorithms fail. So we try to adapt our games model to the dynamic scan to allow some smooth modification. And our model do not use the control points. We use a large Gaussian, which we called core Gaussian, and the sub-Gaussian, the small one. And in general, we first trained some large elements which describe the shape. This Gaussian don't have colors and opacity, only the shape. And we produce the small Gaussian in the local coordinate system of the large Gaussian. So if we move the large Gaussian, all Gaussian which are connected with the core Gaussian move according to the core Gaussian change. And thanks to it, we can modify the large elements to modify elements of the shapes. The model is a little bit complicated. We have this core Gaussian, sub-Gaussian, and two deformation network. The first deformation network controls the core Gaussian and to produce the correct move of to learn how the object is moving. And the second one a little bit changed the small Gaussian, because when we change the large Gaussian, small Gaussian, sub-Gaussian also move, but we additionally add the small one layer to adapt this small Gaussian to produce some small changes in our project. And thanks to it, we can, the scene are moving in general, but we frozen them in some time step, and we can change the shape of the monster. I don't know if you can see, but this guy or something moved the finger. Yeah? You can also move the hand, and we also can multiply this blue ball a lot of time, rescale, and force them to moving according to the original. So this was nice. So we decided we adapt the Gaussian method to the physical engines. We call this GASP. So the idea is to, we can move it by ourselves. We can move it by the neural network. So we also move this Gaussian by physics. Yeah. So the idea is to use some physical engine. And the idea is that we have Gaussian, we can produce these triangles, we can only take this point from these triangles, so we have point clouds. The point clouds can go to the physical engine, which is trained on the point clouds, and after training on point clouds, the physics move this point according to the environment we specify, and everything works with dynamic and static state. Of course, it occurs that each point from the triangles is trained separately. So when the bear goes to the cab and we force the bear to be a sound. Yeah, and when he hit the cab, it occurs that this point goes away, yeah, because they are trained separately. So we have to force them to be a correct Gaussian, and we add some small modifications. And if some points go very fast, we force them to stay close to the center of Gaussians. And thanks to it, we obtain the correct physics engine combined with Gaussian splatting. In practice, we change these triangles up. Yeah, when we change this point of the triangles, in this case, the physical engine changed these points, and we can see the renders which are produced by the Gaussian splatting. The same is in the second example. And in general, this works nice. Here we have some objects fall down and correspond with the scene, and here we have some other physics. Okay, so the next step was, we combine it with dynamics and physics and statics, and so we start to thinking that maybe it is possible to combine with 2D image. So at the input to the model, we have only one image, and we don't have any set of images, and our goal is to modify an image. So we decide that 3D Gaussian can be dedicated for single image and can inherit the, easy modification. And the model is trained in this way that when we have a single image, we put two cameras in the reverse position. The image is inside. On the far side is the cat, and on the second side is a mirror reflection, yeah? Because we want to reconstruct them consistently. So in practice, we train this Gaussian on the plane. Yeah, so we have the flat Gaussian, yeah? We here use, of course, flat Gaussian in our games, and after the training, we can move or modify Gaussian to obtain real-life modification. And you know, this is quite nice because we have the 2D image in the 3D space. So we can modify it according to the 2D space, but we can also use this additional dimension to move them in 3D space. So for example, we can force this flat woman to be almost 3D. So we call it mirror because, I don't know, 2.5 dimensions. And of course, we can combine it also with a physical engine. So this is quite easy or simplified physical engine because it's only 2D physical engine. So we take these points from the triangles into this 2D and add to some physical engine. I don't know why people produce 2D physical engine, but this kind of engine exists, and we can force the 2D image to be dynamic. Okay, and that's all from me. But you know, when people end the talks, always is the question, what's next? So I want to invite you, if you are interested in Gaussian splatting, to work with our teams, and I prepare some project which you can participants of the first project, which already started, is adding our games to the VR engine. There exists some solution which combine Gaussian splatting with VR. They are produced by cages. Yeah, we keep the Gaussian in the cages, and when we move cages, the objects are moved. But these cages are quite not accurate. We think that the triangles or the mesh we estimate are more correctly fitted, and thanks to it, we can work with VR more accurately. We also think about parameterization of Gaussian splatting by neural networks. So it's called INR, implicit neural representation, because Gaussians are quite heavy, yeah? Because we need to use a lot of few 100,000 Gaussian per scene, or few millions if the scene is large. So it's quite heavy. So we think that maybe it is possible to compress in the neural network weights, which convert the position from the sphere into the parameters of Gaussian covariance matrix, position, shape, and something like that. And for example, the third project, you know, when we add some elements from different scenes, I hope you can see that they are not correctly suited, yeah? Because, you know, this DAGs are in not correct color. So, and this is a problem in Gaussian splatting. So we think that maybe it is possible to force this DAGs to be in the correct lights or something like that. And you know, it's quite difficult to do because the Gaussian splatting works on the reconstruction, and we don't have the reconstruction of the DAGs and the scene in the correct color. So we think that we can combine with some GAN as adversarial training, and thanks to it, combine them together. And also the fourth project is that we can combine. We want to combine the Gaussian models with medical images. The mirrors can model a single frame. So if we have a lot of frames, maybe it is possible to model it with Gaussians, and thanks to it, measure some elements in 3D space, or modify it, or allows the people to, you know, prepare some I don't know, simulation about some surgery or something like that. So we think that this can be combined with okay, so maybe one more. So at the end, we want to convert our Gaussians to this slide is here by accident because this project is almost finished. But in general, we want to generalize this Gaussian to the movies. Yeah. So the idea is to produce the Gaussian in 3D space, and when we cut this Gaussian by the planes, by the video frame, we obtain to the case which can be produced by mirrors. Okay, so that's all. Finally, if you are interested with Gaussian, you can find me on the web page, and this is the slide which was announced by David. Thanks a lot.